Alright, so this area studies what's called functions and graphs. So anything which is classed as a function, anything you can draw a graph of fits into this. And the first ones we're doing are circular functions. All right. So graphs of sine and cos, sine x, cos x. That we've already met these briefly in methods. Did you do any in year 11? Oh, you did a bit in Spec 2 in year 11. All right, so our basic one, so y equals sine x. Basic one has a period of 2 pi. It starts at the origin, has a maximum value of 1, a minimum value of -1. A period of 2 pi means it gets back to the same place. Of course, we know it goes up, comes back down, and then back up again. So, and you can also keep going and go back in the opposite direction. I'll just go half a period back in the opposite direction, and so on. And it will continue both ways for as long as you want to draw it. The cos one, very similar. It also has a period of 2 pi. Maximum of 1, minimum of -1. But this time, starting point, we can use as our starting point on the y-axis. Instead of going through the origin, it goes through 1. So 1 period later, gets back up to the top. And then with the sine and cos, we look at two peaks, 2 highest points, and what they're 1 period apart and halfway between is the lowest point. So for cos then, if they're 2 peaks, halfway between is our trough. And of course, halfway between a trough and a peak is where it crosses through the axes. And of course we can continue backwards, and so our cos one, we like to continue it, goes like this. So then there's the basic ones, and then we can transform these, which I'll get to. Give me a minute to get that written down. All right, and I'll rub that off. Alright, so there are our basic ones, and so then we can do transformation from that. All right. And so transformed ones would look like this. Sometimes you might see an extra bracket around there. Sometimes you do, sometimes you don't. Some books and things you'll read won't use H and K, they'll use other symbols. I like to use H and K, because H and K are translations. H in the X direction and K in the Y direction. Alright, so for sine and cos, our period is 2 pi over this n, so this n here is the dilation. Moves it the opposite way to what you would think. Ends up on the bottom. So if n is 5, then it makes it 5 times smaller, not 5 times bigger. So that one's opposite. The amplitude is that distance from that midline through to the top. That's given by this bit here. And the other things I've already mentioned is we've got translations. So a horizontal translation, it's in the X direction, so that's this number here connected with the X. And in our vertical direction, spelled that wrong, got my I and T around anyway. Again. Alright, so our vertical direction is our K. Let's do an example now. You got that? Everyone got that down? Right to rub that off?
Yep.
Right up.
Your camera recording?
I hope so. I bet you it's not. I bet you I forgot to turn it on. Did I forget to turn it on? No, I didn't forget to turn it on. It's on. See, I haven't got the budget like Eddie Wu's got. Toby, Eddie Wu. You know Eddie Wu. He seems that sensation.
Right.
Yeah. So mine's low budget. I haven't quite got the enthusiasm that Eddie Wu's got either. It's not. All right, so let's sketch. All right, there's a couple of things in here. So this first one here, this of course is our domain. So when we are sketching, we've got to have the graph between 0 and all the way to 2 pi.
And the R is range, right?
R is the codomain. And our range fits inside that codomain. Alright, so that brings up a good point, yes. Often you might be asked, particularly in methods, to state the domain of something, and it's not necessarily that number there. Maybe mathematicians were too lazy to work out what the domain was going to be, so they just put, we'll just put R all the time and call it the codomain. Alright, now the other thing with this one here, and all ones like this, for us to correctly be able to follow those translation patterns, etc., whenever you've got something like that, you need to rewrite it. So we need to rewrite it as 3 cos. And then what we need to do is we need to take the 2 out as a common factor of those. Alright, and the reason we need to do that is, as I said, it's so that the pattern fits. So the pattern of the translations and that fits. Alright, so if you don't take the 2 out, that horizontal translation, you can't just read it straight from the...
So you just divide by 2.
Right, by 2, yeah. So, yeah, if you don't take that 2 out as a common factor of those, then that horizontal translation doesn't appear in the function equation as it's written.
Yeah.
So yes, we just divide by 2 in that case. So, before we sketch it, what do we know? Alright, our period is 2 pi on n, 2, let's get rid of the n, 2, which is just pi then. Alright, so it repeats every pi. Amplitude, what's our amplitude?
What does the amplitude mean? Because I said it was the...
So the amplitude...
Is that like the dilation?
Yes, it's a dilation. So it's a dilation in the y, or from the x-axis, if you like. So in y direction, I'll go say.
Because I think I lost some marks in our previous stuff because I said the amplitude was 3 and negative 3 instead of 3.
Yeah, the amplitude is just the number, the 3. If there's a negative in front of that, then that negative is not the amplitude. That negative will be a reflection in the x-axis.
Yeah.
So yes, it's important to the amplitudes. So if I had, for example, if I had minus 3 cos up there, then the amplitude would still be 3, and that minus does a reflection. And so what is it? It's the distance from our midline to the top, or to the crest trough. You go up to the crest and down to the trough by that amount. Does that make sense, or has that confused you?
No, it makes sense.
Makes sense? All right, so we've got some translations. What are our translations? So in the brackets here, the translation is which way? pi on 6 to the left, yep. So pi on 6 to the left. And the other one is 1 up. Alright, so let's sketch this. So this is how I go about sketching. Something like this. Alright, 2 pi and pi. I've got them marked in. I've gone up to 2 pi because of my domain, so I've gone from 0 to 2 pi. Alright, now, because I've got this translation here of pi on 6, what I then like to do is to mark in pi's on 6 in here. And I'll show you why I like to do that in a minute. Alright, so each of those little marks there is pi on 6. Just got this a little bit out of whack, let's not worry about that. Then the next thing that I would do is I say, alright, we've got this translation in 2 ways. We've got a translation up and we've got 1 pi on 6 to the left. So, what I then would do is I go, alright, so this is a cos and we've got an amplitude of 3. So this is a cos. So normally for a cos we're starting at 1, but we're moving to the left and then we're moving up 1, but our amplitude is 3. So what I like to do is this, I like to put in this midline. And say, okay, so rather than working around our x-axis, I'm now going to be working off my midline because I'm going 3 above it, 3 below it. Alright. So, where do we start then? So we would start, instead of there, it's going to be, because we've got an amplitude of 3, then we've got to come 3 above that line and 3 below that line. With me so far?
Yep.
So that would be up there, but when we've got our translation to the left here. Alright. Now, this is why I've divided into pi's on 6. Because our period is pi. How many pi's on 6 is pi?
4,
How many?
6.
6. So if I've divided these into pi's on 6, one period is, I've got to count across 6 of them. So if I count across 6, I'm going 1, 2, 3, 4, 5, 6, and I'm there. And normally I'd be at pi, but we've translated back. There it is. Halfway between those, we've got to have our low point, yes? So halfway between there and there would be 1, 2, 3 pi's on 6. Then, halfway between our minimum and our maximum is where it's going to cross this blue line. So there. Yes, no, maybe?
Yep.
And halfway between there and there, which is here, it's going to cross that blue line. Normally that would be where it's crossed the axis, yeah, but we've moved, translated up one. All right, and then you repeat that. So we got back to here. Where are we? There. 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 All right. Now I've got partly, I've not quite got it. So it's just for, so normally, so we'd be going, okay, well it goes there like that, something like that. But remember our domain is from 0 to 2 pi, so this bit that's down here, well I've done that to help me sketch the graph. We don't actually want that. We're only wanting from here. So on an exam, they might often ask you to work out what f of 0 is. And f of 0 would be that point there, wouldn't it? So whatever f of 0 is, work that out.
You work it out based on your drawing, or?
Well, you would work it out precisely, wouldn't you? Not based on my drawing.
Yeah, right.
You would work. What you should do is work it out and then base your drawing off that. Alright, so I don't know what that is. Cos of pi on 3 is half, isn't it? 3 lots of a half is 3 over 2. Plus another one is 5 over 2, isn't it? Is that right? Which is 2.5, so I've marked it too high up here. About here. Shouldn't it? So that point there is.
And then you go all the way to 2 pi.
And then we've got to go all the way to 2 pi. So f of 2 pi, you can figure that out.
That's
But, sorry?
isn't it just the same?
Well done, Cody. Yes, because remember, a period is not necessarily just from our peak to our peak, or from here to here. A period is anywhere on a corresponding spot. So there to there is a period. All right, and because we've started here, and pi later, there we are, another pi later, there we are again. So that point there is 2 pi 5 over 2. And of course you should always label those endpoints.
Label the endpoint.
Should always label them, yeah. Don't give the examiners any reason not to give you all the marks, Toby.
Fair enough.
Yep. All the markers, I should say, not the examiners, the markers. Don't give the markers any reason not to give you full marks. All right. So, next I have a couple of sheets. Should stick these in your band reference. In terms of remembering these sheets, me personally have never remembered these sheets. I've always just worked them out, worked out what I need to work out when I need to work it out, rather than just using the unit circle. So the exact values, so you're expected to know exact values. So for pi on 6, pi on 4, pi on 3, pi on 2, pi, 3 pi on 2, 2 pi, you're expected to know the sine, cos and the tan of those. And then if you know those, you can then work out all the others in all the other quadrants. So that big long list there shows you all the quadrants. But if you know the first quadrant, you can work it all out. Same with the symmetry properties. There's the handout there. I'd stick it in around reference to use it in exam 2 if you need to. But as far as committing to memory, it's a lot of stuff to commit to memory. So again, as I said, I just work out what I need to work out using the unit circle and drawing time. So the triangles, yes, Tate.
Or stuff like sine of 45 degrees or sine pi on 4.
Yep.
For some reason in special, I just remember it always being 1 over root 2. It's got to be 2.
Root 2 on 2.
2 on 2.
As far as I'm aware, and I don't know if this has changed, VCAR always wants rational denominators.
Yeah.
So it doesn't matter what you work with, just as your final answer. Make sure that you have a rational denominator. But if you remember it as 1 on root 2, it's not like any big deal. Just remember your final answer. Have it rationalised. Alright, any other questions about that? Alright, okay, our next thing then is what's known as the Pythagorean identity. So the Pythagorean identity. And the Pythagorean identity is this. It says that sine squared theta plus cos squared theta is equal to 1. Now there are some variants. So one of our variants we get if we divide everything by cos squared theta. And this 1 on cos squared theta, this 1 on cos, is known as sec. So 1 on cos is known as sec or secant or whatever. Now your calculator, depending on what you might have on it, doesn't have sec theta, so if you always got to enter as 1 on cos in your calculator. There may be a way that you can do the sec on the calculator, but if there is, I'm not aware of it. Right, so just be aware of that. Now the other variant you get when you divide everything by sine squared. Oops. And so when you rewrite that, sine on sine is 1, cos squared on sine squared. Whenever you have cos on sine, it's called cot. And then 1 on sine is cosec. So cos theta over sine theta is cot theta, which is also incidentally 1 over tan. And as I said, 1 on sine theta is cosec theta. All right, got that? We're good with that? Can I can rub that off? Yeah. All right, let's do a couple of examples of this. So we can use these sorts of things when you get given, say, you're told that sine of x degrees is equal to 0.3 and 0 and x is between 0 and 90. And we want to find some stuff. Alright, so in this we don't need to work out what that angle is. We don't need to work out x. We've been given the sine, and cos and tan relate to sine. So this is where our Pythagorean identity comes in, because cos squared x plus sine squared x is equal to 1. So put in the numbers, cos squared x plus 0.3 squared is equal to 1. 0.3 squared is 0.09, correct. Take 0.09 from both sides. That. And so cos squared x would be 0.99, is it? Oh, 91, not 99. Oh, I made a mistake. All right, so we then need to square root that, so we get our calculator to do that for us. So that'll be plus or minus something. And plus or minus 0.9539 is what our calculator gives us. I'm going to go 2 decimal places with that. Now, do I need the plus and the minus, or do I need just one of them? All right, which one do I need and why?
Because it's
All right, first quadrant. Oops. So first quadrant, our angle. So cos in the first quadrant is
plus.
plus.
Do you write the plus in front of it, or do you just say?
No, you don't need to. I am just to emphasise that it's positive because it's the first quadrant. All right. Then once you have that, we can now find the sine, the tan I should say, because tan x is sine x on cos x. So the sine we were given at 0.3, we've just figured out 0.95, and on the exams they'll always indicate how many decimal places if it's a decimal. If it's not a if they don't do that, then they probably want it in an exact value. And sometimes they'll even tell you what form otherwise they'll just say put it in this particular form. All right, so 0.3 divided by 0.95. Has anyone got your calculator out there and figured that out?
0.3157.
3157. So it seems I've used 2 there. So I'll go 0.32.
In the exam, you have to write true DT in brackets.
No, because they will ask you in the exam
Yeah.
to do it to a certain number of decimal places. So if they say give your answer to 2 decimal places, then you don't need to do that at all. And so, like, if they ask you a particular thing in the exam, and I'll give you an example from further maths. One of the questions in the exam was what percentage does this particular thing affect the other one, to what percentage? So because they'd already asked what percentage, you didn't actually need to, in the answer, put the percentage bit in. All you needed was the number. So if it was 20%, all you needed was the 20 because they've already asked and indicated that it's a percentage. So if they've already asked something and indicated something, you don't need to tell them again. That number's representing what they've asked you to do. All right. All right. Equations. Everyone loves trig equations, don't they? Did a little bit of this in methods, and you guys, I know in units 1, 2 special did this as well. So I'll do one example. All right. So there's a few bits and pieces in this. First of all, I'm looking at the sine of whatever this here is. It's a half, so it's positive. And what that indicates is that we're looking at the first and second quadrants. Because that's where sine is positive. So the way I do it is I always do myself a rough sketch and I always go, so now I'm looking at first and second quadrants. So I'm looking at this angle here and this one around there, and I need to figure something out about it. So what do I need to figure something out about it? Is I now need to look at the half. And the inverse sine of a half, or what angle, if you like, is a half, either one you want to do it. Sine -1.5, however you want to look at that. And the angle that has a sine value of a half is pi on 6. So that's what I would call the reference angle. Because all the other angles are all related in some way to that angle. And, not by coincidence, that reference angle is this angle between our line, small angle between our line and the x-axis. So this here is pi on 6. And there. Alright. So far, so good. The next bit we've got to do is we've got to look at the angle. So here we've got 2x plus pi on 3 is we're taking the sine off. But over here it's just telling us about what the domain is for x. So the easiest way for me to deal with this is to change this domain for x to fit this here. So 2x, you simply multiply both of those by 2. So 2x is between that and 4 pi. Then add pi on 3. So we're going between pi on 3 and 4 pi plus pi on 3. And you can work that out if you want, but you don't need to. Alright, so what does that mean? So we're going between pi and 3. So pi on 3 would be around there. And 4 pi plus pi on 3. So we're going from here pi is twice around the circle, yeah? So from there to 1, 2, there. So any time an angle fits into there, we need to write it down. So now and I'll get back to the x later, but at the moment I'm working with the 2x plus pi on 3. Alright, so the first one, start here, get to there, pi on 6. Pi on 6 is not in our domain, yeah? So we haven't got to there yet, so pi on 6 is not. Here to there, pi minus pi on 6, that fits in alright. Because that'd be 5 pi on 6, wouldn't it? So that fits in. Alright, so then next one, keep going. Around a whole circle, plus pi on 3, that fits in. And so what's that? 6, 7 pi on 3? No, sorry, pi on 6, not pi on 3.
7 pi.
Oh, sorry. So I'm going 2 pi plus pi on 6, not pi on 3.
So 13.
So I've got the wrong number there. Sorry. 2 pi plus pi on 6, isn't it? The reference angle's pi on 6, not pi on 3. Alright, so 13 pi on 6. Alright, what else can we do? Alright, so we've been around to there. We can go around and keep coming around to here. Well, that'd be 3 pi if we got to there, minus the pi on 6, wouldn't it? Uh, 18 minus 1, 17. And then there's one more, because we're allowed to go 1 pi, 2 pi, plus the pi, 1, 2, 2 pi, 4 pi plus the pi on 6. 25 pi on 6. Alright, and now we've just got some mucking around with some arithmetic. Mucking around with some arithmetic. Because this is pi's on 6s, I'm going to change that to 2 pi on 6. Because what have I got to do? We want x, because it asks us to solve for x between them. So first step, I need to move this pi on 3, so I've got to take it away. Yep. So remember, pi on 3 is 2 lots of pi on 6. So what have I got to do with these numbers on the top? Take how much?
Take 2 pi.
Take 2. So 3 pi on 6. 11 pi on 6. 15 pi on 6. And 24 pi on 6. 23. 23, glad someone's paying attention. Alright. Then you've got to move this 2. I move the 2. And so when I move the 2, I've got to divide by 2. So what happens to my denominators? 8 times the denominator by 2, so my denominators become 12ths. And at this point, cancel down what you can. On 4, I think that one is. 11 pi on 12, nothing you can do there. 15 pi, 5 pi on 4, and nothing we can do there. There's our 4 answers. Alright, bit of mucking around. Now, in exam 1, you have to do it by hand, but in exam 2, you have your calculator at your disposal. So let me show you how we can do this on our calculator. So first thing is, what's our angle measured in? What units? What units are they?
Radians.
Radians. So make sure you've got rad here. The other thing is, these are exact answers, so you need to make sure that you have this not as decimal but as standard. So click on that, standard, there it is. And then we can ask the calculator to solve. Now there's a few different ways you can get to the solve. You can get it from action advanced, you can get it there, you can get it interactive advanced, you can get it there. You can also get it off your keyboard in Math 1. Right. Going to need my keyboard later, so I'll get to it from there. It doesn't matter which one you use. Alright, so what do we want to solve? We want to solve that equation, and that equation is sine of 2x plus pi on 3. Whoops. Let's go back, go down, pi on 3, across, close bracket. Equals what? Equals half. What do I want to solve for? I want to solve for x. Often it doesn't matter whether you do that or not. But I always like to do that just in case. Now,
Don't you put the domain in?
that's what I was going to get to, Toby. Exactly, fantastic. Because if you now go EXE, don't be sorry, Toby. Because if you now go EXE, you get this, all this stuff, pi times some constant, blah, 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 blah. They would be general solutions, so if you didn't have a restricted domain. But as Toby has already pointed out, we've got a domain between 0 and 2 pi. So we can put that in. So at Math 3 tab, this vertical line is the domain, and the domain is between 0, square brackets, less than or equal to, x less than or equal to 2 pi. So now when we go EXE, now it's going to give us any answers between 0 and 2 pi rather than just a general solution. There they are. Pi on 4, 5 pi on 4, 11 pi on 12, 23 pi on 12. All right. Last thing for today is tan graphs. Alright, so it's a graph of tan. Alright, similar form, but it's tan instead of sine and cos. So our period, here's where the difference is. Tan repeats itself every pi. So the period's pi on n rather than 2 pi on n for sine and cos. It's pi on n. So the dilation in the y direction. Toby asked before about that with the sine and the cos. The amplitude, yes, the amplitude is also a dilation in the y direction. It's true, but we don't actually have an amplitude in the tan graph because it doesn't kind of get to a high point and then come back. So it's a dilation in the y direction, and that's by A. And then our translations are H and K. As before. So our standard, which I'm going to do over here, our standard y equals tan x will look like this. So I'm just going to do one period of it. Well, actually, I'm doing 2 periods on each wave. Key thing about that I haven't written that I will write, I won't write in a minute at all, is that tan has some asymptotes because the tan of pi on 2, 3 pi on 2 and so on are undefined, so we have some asymptotes. Now the key thing, as before, we talk about a period being from one point to corresponding in the next cycle. So for your normal standard tan, it's not just a random thing that they're pi apart. So you have 1 pi on 2 and negative pi on 2. The tan of 0 is 0. The tan of pi on 4 is 1. And negative pi on 4 is negative 1. So those 2 points are out there, our key points, and goes like that. And over here, we've got the next bit. So come up there, and then the next bit down here. And coming back the other way, we've got the next bit, and the next bit is this one. Example. Alright. Period, what's our period? On to repeats. Translations. On 4 to the left.
Isn't it? I know, don't worry.
And up 1. Dotted horizontal line. So it might be handy with this one to know what's going on the y-axis. Alright, because you can get confused. So just to help us, when x is equal to 0, we would have tan 2 lots of 0 plus, oops, sorry, another bad. 2 at the front of 0 plus pi on 4 plus the 1. 0 plus pi on 4 is pi on 4. Oops. So we've got tan of 2 lots of pi on 4 plus 1. And 2 lots of pi on 4 are pi on what? On 2, aren't they?
Yeah.
What do we know about pi on 2? It's undefined. So if pi on 2 is undefined, what does that mean about what's going on at x equals 0? We have a, starts with a asymptote. Alright? So we have an asymptote on the y-axis. I'm going to draw my asymptotes in green. So if I have one of them there on the y-axis, when would our next one be? How much later?
1 period.
1 period later, which is pi on 2. So we'll have another one here. And after that, we'll have another one. 1 period later, pi on 2. Now, what happens halfway between our asymptotes? So halfway is where it crosses that midline, if you like. And because we've been translated up 1, halfway between those is where it crosses that point there. Yes? Am I right?
Yeah.
Alright. Now, halfway between there and that asymptote, normally it's going to be up 1 higher. But in this case, we've got a, and I didn't write it down, did I? We've got a dilation. Oops, can't spell. Of 2. So if it's a dilation of 2, it's not going to be up here at 2, it's going to be up at 3.
Wait, why is there
Oh, no, sorry, my bad. Oh, there's no dilation. Ugh.
Yeah.
What am I talking about? Lucky I've got you here, Toby. So if there was a dilation, yeah, we would have to, but there's no dilation, so it's one up here, over this way it's one below, one above, and so we get something like this. Ooh, put that in the wrong spot, there you go. There it is. Alright. Whoops. I nearly made a tragic error. Alright, anything you want me to clarify there? No. Alright. Well, that will do. You also on your work plan, that's the first lot of stuff.